Okay, let's have a quick look here. It may not be all the way done, but hopefully at least you got your table built and you got to start on this. All right, so what do we do? Building our table. How do I build my table? Okay, I need the x-axis, right? So here's top of the table is just the x-axis. Our tables in Algebra 2 have 2 rows. In calculus, they'll have more than that. Okay, so what can we add to our table here? What are some things we know? What are the zeros of this, the x-intercepts? 3, 1, and -6. And we get those from the distinct factors, right? There are 3 distinct factors involving x, and so that means we're going to get 3 x-intercepts, right? Everybody agree? Okay. So what did we say they were? -6. In order, they'd go -6, 1, and 3. Okay. And what do I put in the y row with those? 0, because they're x-intercepts, right? We get those by setting our function equal to 0 and solving the equation, right? Okay, and then we know that by the zero product property, those are the 3 solutions we get by the zero product property, okay? So we can write those as ordered pairs, and those are 3 points that we know. So we can already start to build our sketch a little bit, right? So let's see, y-axis, go right about there, I guess. Okay, so there are our 3 x-intercepts. What else should we add to our table?
And behavior.
And behavior. Good. Okay, so what's the domain of any polynomial? All reals. Good. They're well behaved. No issues. So we can write our domain on that upper line. I'm going to put rounded brackets and negative infinity all the way up to possibly infinity. Let's go back. Looks like an 8. Okay, so let's try out our end behavior then, right? We already know when we find end behavior that the limit of f of x as x approaches, for example, positive infinity is going to be infinite. We just need to know what kind of sign, right? So let's see what we get. How many factors, total factors, not just factors involving variables, but how many total factors are there? How many things are being multiplied together in our function? 4, because we get a constant factor and then 3 factors involving variables, right? 3 distinct factors involving variables. So we just have to look at the sign of each of those to determine the overall sign, right? Okay, so let's see here. Emily, what's the sign of the first factor? Negative, right? There it is. So that one's negative. Is it going to change? No, it's constant, right? It's going to be the same regardless of what we evaluate our function at. It's always going to be the same. So I'm going to make that one, how about if we make that one red to indicate it's not changing? Are there any other factors up there? Let's get into this a little deeper than we did last week. Are there any other factors up there whose sign is always going to stay the same?
X plus 6, as I was going to say.
Okay, and that's, how come?
Because you can't get a negative number from adding 2 positive.
But what's the, you're right, what's the part of that though that's telling us it's never going to change? It's squared, good. Because this one is being squared, any number squared is always non-negative, right? Okay. So then that's telling us that this guy is going to be positive no matter what. The ones in between, though, might change, right? Well, when we're evaluating at a huge positive number, what's gonna be the sign of this guy? Positive. What's the sign of that guy? So what's the overall sign? Negative, right? Because I've got an odd number of negatives being multiplied, just one of them. So I'm gonna get negative infinity. So the end behavior here is negative infinity, right? Question? Because a huge positive number, like positive infinity minus 3 is positive infinity. Positive infinity minus 1, positive infinity, right?
What if the number that's like minus a million thousand bajillion?
Wouldn't matter, because this is approaching infinity. So nothing, you could never subtract anything from it that's ever gonna change its sign.
Okay.
Right? Yep.
So to like find when it goes back down and stuff, do you just replace the positive infinity with a number? Like the F in parentheses positive infinity?
You mean when we do the test points?
Yeah.
Yeah, we will, absolutely, yeah.
Wait, how
Yeah.
do we know which is like by positive infinity or something like that?
How do we know what now?
How do we know like if it is positive?
Well, because we're evaluating the endpoints, right? The end behavior, not endpoints, the end behavior. So we want to know what is the function doing as x approaches positive infinity. We know it's going to be infinite, right? It's got to go, it has to, right? Because that polynomials do that. Polynomials are always going to go up forever or down forever, right? And we can see that pretty easily, because look what I'm doing here. I'm taking infinity times infinity squared. We know we're getting huge numbers, but we just got to know, is it going to be a positive or a negative? Yes, ma'am.
So when we get the negative on the end, that means when the x is going like this way, the y is dropping down.
Yeah, so when we go forever out to the right, we're looking at the right tails of the function. We're going to go down.
Okay.
Yeah, and so that tells us something important. Over here, then, we could do this. We know that the end behavior is going to be down, right? Yes.
But how do we know that it's positive?
Well, because we asked it.
Because x, it's going, so we start there, and then once it goes to the positive side, so it's moving this way.
It's going that way more.
So positive infinity is the x on the top, the positive infinity is this way. So while it's moving this way, the y part's dropping down.
See, we're saying as x approaches infinity, f of x approaches what? This is our more sophisticated way of saying what in the book they would have said as, in our textbook, they would have said as x approaches positive infinity, f of x approaches blank, and that's what we're answering. But this is the way we should write it. This is the calculus way of writing it. Same thing, means exactly the same thing, right?
So if it was as f of x approaches negative.
Which we have to do also, right? We need both. So we got to do f of negative infinity equals what? We got to know, right? So we already said that the first factor is always negative, the last factor is always positive, but what about the ones in the middle now? Negative infinity minus 3 is negative, right? And understand, when I say negative infinity, you can't really do that, but it's just we're approaching infinitely big, right? Huge, huge negative numbers. Negative infinity minus 1 is negative, so what do we get? Negative. We get an odd number of negatives multiplied together, right? So then we know that the end behavior at this side is also down.
Wait,
Right?
what makes the last one positive?
Because it's being squared.
Oh, okay.
Yeah. All right, so then that's helps us a ton. Now we need to know what's going on in between the zeros, though, right? We know that. Let's kind of, once again, let's ramp this up one notch from last week. What's always going to happen between zeros on a polynomial? Always. Something has to happen between zeros. Say it again.
It either goes up or down.
Good, and it's got to turn, doesn't it? Right? So we know that we have to get turning points between the zeros. Because if this just makes sense, right? If the polynomial is going to go through this x-intercept and be up here somewhere, well, it's got to get down to there again, right? Because there's another x-intercept, so it's going to have to turn, right? So we know that there are always going to be internal turning points. Later on, and like I say, in calculus, we'll we'll take this to a whole different level where we'll actually be able to use calculus to go find the values, the x values, where those turning points occur, right? But that's a couple years down the line. For now, we have to use graphing technology for that stuff. So let's try some test points. We want to find the most convenient test points we can. What's going to be the most convenient test number between -6 and 1? 0, for sure. It's going to be 0. So at 0, thank you. At 0, what are we going to get for our sign? Well, we'll do the same kind of thing we just did before, right, up here with the infinities. F of 0 is going to equal what? Who's going to know the sign? We don't even know the value. Well, we already know that the first and the last factors, the signs are fixed. What about the middle ones, though? 0 minus 3 is negative, 0 minus 1 is, so the overall sign is negative, because I got 3 negatives there, right? Okay, so we got a test point below the x-axis between -6 and 1, right? We got to check another one, though. We've got to look at a test point between these two zeros. What's a convenient number? 2. Okay, so we'll try f of 2. Okay, we already know that's negative and that's positive. No sense even wasting time on those. 2 minus 3 is, 2 minus 1 is, so now we get an even number of negatives, so we're positive, okay? And that's all we need to do our sketch, right? So we know we're going to get, in here we're going to get a positive, in here we're going to get a negative. What could you tell me, once again, let's take this up one level. What could you tell me about how the magnitude of the turning points here, which one's going to be bigger of these two? This one, or which is going to be further from the x-axis? Yep, this one is, right? Has to be, doesn't it? How come? Can you tell me why?
6 to 1 is bigger than.
Yeah, that's right. It has something to do with, think about the magnitudes of these numbers that are being multiplied, right? Because like when we're going down here to something like 2, 2 isn't very far from 3, is it? 2 isn't very far from 1. So the numbers that are being multiplied together there are pretty small, right? But the distance between 1 and -6 is pretty large, right? And so when we plug in numbers there, like for example, let's just take a number like -2. -2 is 3 away from 1. -2 is 4 away from -6. We're multiplying bigger numbers together, so what's that going to do to the amplitude of the function? It's going to make it bigger. Also, this one's even being squared, right? Do you see that? So that's something we can say in general about polynomials. We can say in general that when x-intercepts are further apart, that means we're going to get bigger peaks and valleys between them, right? I mean, it's not, and this isn't, is that crucial information for Algebra 2? No, not at all. But you guys are kind of looking math, you get different trajectories in math than maybe just plain old Algebra 2, and so I want you to be thinking about this stuff a little bit. So this one we could expect to be down a little bit lower, right? For purposes of a sketch, not a big deal. It's really not a big deal, but just be aware of that. So if we add that to our end behavior then, so this is going to be downward behavior, what does the function have to do over here? Okay, it's going to go, so we know that it's going to go from here, it's going to go down below. What's it going to do at this x-intercept if it's got to end up with negative end behavior? It's got to be tangential, doesn't it? Okay, so it's got to come up and do something like that. Right? How about at this end? If it's going to end with negative end behavior, what's it doing over here? Okay, it's just going to cross, like so. Right? There's our function. Now let's go back and let's put phones away, please. Let's go back and see if we could have maybe, you guys are getting to a point where your intuition is growing rapidly here about this stuff. Could we have maybe gotten to this point without even having to do the table? And I want you to do the table. I mean, that's on the assignment, that's expected. But Could we have maybe finessed our way through this? Probably, right? Probably. If I were to expand out this polynomial, what's going to be the degree of the polynomial if we were to write it in standard form? It's going to be x to the what power? Not -4. +4. The coefficient's going to be negative, but if you look at what the powers of x are going to be, if I expand that out, my biggest power of x is going to be x plus 6 squared. If I expand it out, is going to give me what's my biggest power of x? X squared, right? And some other junk we don't care about. If I multiply that by this guy, it's going to jump it up to x cubed, x to the 4th, plus a bunch of other garbage that we don't care about. And then the leading coefficient is negative, right? So we could summarize this function by looking at, for the end behavior purposes, by looking at its leading term. Remember how we looked at that? You guys remember when we zoomed out on that function, and the only one that mattered was the leading term. So this is summarized by the leading term. So we could say, let's go down. So we could say f of x equals negative x to the 4th plus, who cares? When we're looking at our end behavior, right? We know this is going to be, the end behavior is going to be an even function that's been flipped downwards, right? You get that? X to the 4th is an even function, so it's going to have reflective symmetry about the y-axis. The negative coefficient has taken that normal even function and flipped it around. So that tells us the end behavior is going to be negative on both ends, doesn't it? Right? Right away we know that. We also know that there are going to be, because there are 3 distinct factors, 3 x-intercepts, right? Okay, but what about one of those x-intercepts is going to be different because it's being, that factor's being squared?
Tangent.
It's going to be tangent, isn't it? Right? And that's something we know whenever, let's try to talk about, once again, why it's a little more sophisticated, but you guys can handle this. Why is that one tangent instead of just cutting through the x-axis? You know, Ruby? If we think about what's going on, like let's look at this guy right here, x minus 3. So we know that we have an x-intercept at 3, right? But x minus 3 is a linear function by itself, isn't it? Right? Does that make sense? So as we move away from a value of 3, the amount that y is changing is going to be linear, right? So we'd expect it to change pretty quickly, right? If I pull up, and you got to really focus on this because this is kind of a, I really want you guys to see this, and you're fully capable of seeing this, but it's not like it's just super easy. Okay, so we've seen this a bunch. If we zoom in on this, notice what the behavior is, that the red function, which is the linear function, right, taken to the first power, as we move away from x equals 0, it's growing or shrinking. It's growing in the positive or negative direction just as fast as it always will, right? Everybody agree? But if I look at one of these higher functions, and let's just take x cubed as an example, doesn't do that, right? If we look at this one, we notice that initially it grows very slowly and eventually it grows much faster, right? Why is that? Because if we take values less than 1 to a higher power, what do? Like, for example, 0.1. They get smaller, don't they, right? If you take a number whose absolute value is less than 1 to a higher power, take it to some power, it's not going to grow, it's going to shrink, right? Like even like 0.9. 0.9 squared is 0.81. It gets smaller because you're only taking 9/10 of 9/10, right? Now once we pass 1, that all changes, right? Then they start to grow more rapidly. But close to 0, all of those have really small values, right? They're actually getting smaller and smaller, right? So let's compare that to what's going on in our graph, right? So in our graph, if we think about the behavior around x equals 3, well, we would expect the function's value to grow pretty rapidly, positive or negative, because that's linear. But when we get up to x plus 6 quantity squared, now that's going to behave like a higher polynomial, right? Like a higher power function, like a squared function. So as values move to the left or the right very slightly from -6, what should happen? Well, this factor is going to end up getting much smaller. Like if we put in, for example, -6.1. -6.1 plus 6 is 0.1, right? Squared is 0.01. It gets really small. So that's going to cause the value of the function to get much smaller. Did everybody see that? That's why we get that tangent behavior, right? Because it's not going to change, the value's not going to grow very fast right around that 0, because as we'll say later in the module or in the unit, it's got a multiplicity higher than 1, meaning it's multiplied by itself. It's got a power greater than 1. Does that make sense? Can you kind of put those together? Because that's a pretty sophisticated line of thinking. That's more of a calculus way of looking at things, but hopefully that sort of makes sense. You get a little bit extra intuition from that. So we know then that this has got to be a tangential one, right? And this one, these two have to be cutting the x-axis types of zeros. And so we could have built this function without even the table, really, couldn't we? Right? We know what the end behavior is. What's the only way we could put these pieces together? If we have negative end behavior here, negative end behavior here, a tangential x-intercept here, and a tangential, we'll go with that. A tangential x-intercept there, and cutting the x-intercept, or cutting the x-axis intercepts there. That's the only kind of picture we could have drawn, isn't it? Really, there's no other alternative. Okay, make sense? Okay. The other thing I want to do while we're on this, and I know this probably seems like I'm just beating a dead horse here, but there's something that you guys had a little bit of a tough time with back in module 3 and 4. And I can alleviate any problems by talking about this stuff just a little bit more. If we look at something like this guy, how about this one? Okay, how many distinct, let's just talk about what the sketch would be like here. How many distinct factors do we have? 4, right? X minus 6, x minus 3, and x plus 2. What are the x-intercepts going to be?
0.
Okay, stop. 0. Where'd you get the 0 from? This is important. That guy, right, that guy. And then there were some problems here. Hopefully this will make things a lot clearer. When we went back to like module 3, for example, when you guys were solving quadratic equations, there were some issues when you had something like, for example, let's just say you had negative 2x squared plus 4x equals 0. People had kind of a hard time with this because it didn't look like it had all 3 terms, and so the quadratic formula seemed a little bit strange, and maybe finding magic numbers seemed a little bit strange, right, if we're trying to factor it. But in actuality, it's much easier than all that, isn't it? You don't have to mess with finding magic numbers or the quadratic formula. What would we do to solve this? Just talk to me about the steps we would do to solve this. What's one thing we could do to make things easier right from the beginning? We could say it again. How about divide by -2, right? If we divide everything by -2, then this term is going to become x squared. What's this one going to become? Minus 2x equals 0. We don't really need to add a 0. What's our next step going to be? What am I gonna do? Okay. Okay, so you're talking about maybe completing the square or something, right? There's an easier way. This is the easiest kind of factoring problem you can get. Hello? Yep, we'll do. Okay, bye. Pick up your instrument on the way to band. So notice here that I've got an x in both of these two factors, right? And so what we always want to do is we want to always ask the question, can I factor out a GCF, the greatest common factor? I can't. Right? What's my greatest common factor here? What's the biggest thing that divides into x squared and x? Negative 2x. What could I undistribute, in other words? An x, right? Does that make sense? Now, you guys, I think maybe what you're thinking about is only the number part of the greatest common factor. Well, we could have taken out a negative 2, but we already divided both sides by negative 2, right? We can divide both sides of an equation by a constant, and that's fine. We just can't divide both sides by a variable, right? But now we want to ask, what's the biggest thing that divides into x squared and 2x? Well, x does, right? And here's the proof. What is x squared divided by x? X, right? By our properties of exponents, x squared, x to the 2 over x to the 1 is x. What is 2x divided by x? 2, right? So x divides evenly into both of those terms. We always want to see if I can undistribute something, because look how much easier that makes it. If I undistribute or factor out an x, look what I get. I get x times what's left over when I undistribute the x, or divide each term by x. X minus 2, right? That's our goal. Our only goal here is to get this thing factored. Right? We want to do it the easiest way possible, so then we can use the zero product property, like we're doing here. Right? Now you guys know that this means we're going to get an x-intercept of 0, right? Or in a solution of 0, which is the whole point of this thing, right? So this is actually a super easy problem if you look at it that way. We're just trying to get it factored, and all we have to do to factor it is factor out a greatest common factor from here of x, right? And then we know what our x-intercepts are, aka our zeros, which would be the solutions of this kind of a problem, trying to solve the equation, right? Does that make sense? And I think, this is something that maybe we didn't do a ton of this in Algebra 1. It's kind of assumed in this book that you guys have done a lot of this, but maybe you didn't, right? But I just want to make sure that's clear. Okay? All right.